So I'm going to talk about a paper that Sonlan published on Mantle serpentinization hydrogen fluxes at the North Atlantic magma pure margins. Okay. As you know, natural hydrogen is having a huge momentum now because it's coming a strong commodity will be more and more in the coming years. And now we have this interest now in evaluating how are the natural occurrences of hydrogen. Actually, when we started to work on hydrogen, it was before this wave of interest and was more related in connection to the microbial life, because we were working, so basically we were working in an environmental center, and we are interested in the connection between hydrogen and the initiation of life, so microbial life. This was basically our major interest when we started this kind of work a few years ago. Okay. So here, what Sonlan did was to do a preliminary study of the evaluation of how much hydrogen occurs in magma pure margins. So for this, what he first did was to evaluate all the area that is pertaining to this kind of domain, the continent-ocean transition in the North Atlantic. And then he evaluated how much hydrogen we can produce per cubic meter of material. And then with the global estimate of the areas and how much hydrogen we can produce locally, he made this extrapolation of measurements. So this is a summary of the profiles he evaluated at this point. And you can see the seismic lines available, and the green colors are showing the part of exhumed mantle. And with this exhumed mantle, he did this calculation and made the extrapolation procedure, and he calculated that overall in the North Atlantic we have this 8 to 10 to the power of 5 square kilometers of area which are potentially subject to serpentinization and production of hydrogen. So this is the first step. So the calculation of the area, and then the next step is to, as I said, is to calculate how much hydrogen we can produce locally. So as we know from previous studies, this serpentinization, first what it needs is water. We need a protholite, which is adequate, and we need water. So the water, we understand that it mostly comes down through major fractures and faults. Basically, what the data in which Sonlan was based was some data previously obtained for the West Iberia margin. Specifically, he was focusing in a previous study that another person was Elmar Alberts, also based in Marum, in our group, did before. So he modeled a section here, and this is the section that we'll show you later, and he used for the extrapolation of the estimates, right? So if we go on, important thing here in this kind of settings is how they differ from mid-ocean ridges. If we look at the local productivity that we may have, an important difference is that in the subcontinental lithospheric margin, what we have is mostly litholytic material. And this litholytic material is rich in silica, alumina, calcium, and sodium. And the importance of this is that it displays the equilibrium reactions in a way that the optimal windows for production of the oxidation of the iron and reduction of hydrogen are different than if we move to more depleted mantles towards the ocean. So basically, if we focus on the COT, the area where we produce the serpentinization is roughly in the 8 to 15 kilometers. Is a bit deeper than the area in the mid-ocean region in slow conditions, and the range of temperatures is smaller in general. I'm talking about the range of temperatures for optimal production. The corresponding amount of serpentinite ranges in these values. Okay, so the mean value of this is a K value that will be back to this is 210 millimoles per kilogram of transformed olivine. So if we go to slow and ultra slow, we see that a major difference is that all the main iron 3 hosting phase in slow comes in magnetite. And this is related to high temperature metamorphic reaction, hydrations. While here, the main hosting phase of iron is still serpentinite. Okay, this is a quite important thing. It's important because when we are in these cold environments, all this hydrogen is connected to colder waters and is connected to the isotherm, which controls the limiters of life. So it has a strong connectivity with biochemical reactions. And this is why we are interested in these kind of environments. So next step, once we know where we are moving, is the estimate of how deep goes the serpentinization. So was on landed he was very careful to match his models with some observations, with sustainability profiles. And he was focusing, as I said before, in the West Siberia margin. And we have an example here from Ingo Greve-Meyer from a paper in geology a couple of years ago. And he observes that the serpentinization can reach up to 6 kilometers depth. So Lang takes good care of matching basically this kind of profiles. So I'm moving forward. So in a nutshell, his model setup is a model in which he has it's a dynamic model. He started with 3 layers, with a wet anorthite crust, and with with a dry olivine, sorry, and then with another layer of wet olivine. And then yes, he has stretched until he produced the COT. And he for the transformation of olivine into serpentinite, he used this kinetic ratio, which is from a previous paper from Malbois-Jean, I think 2017. So in which we have this reaction rate as a function of temperature, which is optimal at 280 or so. And then he also put another control. So what he said is that he was only producing serpentinite for areas where the plastic strain rate and the plastic strain were over a threshold and was an unlogical operator. So he had to meet the 2 conditions at the same time. So in a way that basically the serpentinization focused on the major fractures and faults. Well, this is an example of the geophysical profiles that he was matching in these experiments. Well, another thing what I haven't said is that he put a feedback on serpentinization. So he put a weaker rheology. So there's a positive mechanism in which when you produce serpentinite, you make it weaker, and you extract the fault. Okay, so next step. Okay.
You got 10 minutes.
Okay, thank you. Okay, so basically he considered three different reactions. He considered that high temperature reaction in which all iron goes to magnetite. No, you see the magnetite contains the iron 3 portion of the reaction. You part from olivine plus water, and you create serpentinite plus brucite plus magnetite plus hydrogen, right? And he also considered some other reactions, which are the low temperature reactions, in which instead of this magnetite, the iron goes into zingerite or goes into kronstedtite. Then he considered, he was doing some analysis of the ranges of temperature, and he considered that it did not worth to consider the temperature as it's a specific node, but he evaluated that basically to get a mean of these values was enough to get a reasonable estimates. So he said that 2/3 of the reactions were under this equation, 1/3 under this equation, 1/3 under this equation. And then he considered, and according to previous studies, that this is only for the initial serpentinization. This does not consider later reactions of metasomatism or conversion of magnetite into hematite or goethite, for example. No, these reactions are not considered here. So this is what we got. The important thing is that basically, after all these calculations, he became with a magic number, and this number is 227 millimoles of hydrogen per kilograms of olivine, which matches the previous study, the average of a previous study that I showed by Elmar Albers a couple of years ago. So, and then here, what he saw is that there is a coupling between the tectonic of the systems and the generation of serpentinite. This makes sense because you think about that when you have a fault. The fault brings new material to the surface and creates a blob of new material that can be subjected to serpentinization. And then when it is transitioning into the new fault, it goes down, and then we have this coupling. So in this model, basically he started with crustal thinning, and these ocean wall faults, and then started with a symmetrical phase of mantle exhumation, where you can see all this phase. After that, this came into another different regime in the end, in which he entered in this flip-flop mechanism that you all know. So in summary, we go into this. I'll show a brief movie, if this works, that this is kind of showing this connection. So what you can see, basically, when you go high, is because we have a fault, and we have this blob of serpentinite forming at the time. So this is this connection. Still, he did not evaluate the local anomalies of serpentinization. He just calculated the global amounts. Okay, because he was not interested at this point in saying how much of this area is having so much, but having a global estimate only. So basically, you can see, and this goes like that, and in the end, you can relate this mechanism. So further test that he did was an evaluation of what happened if we did not have or had some emulation of hydrothermal cooling. So here you have a summary of some analysis that he did at several extension rates. And you can see that with higher extension rate, you have a higher production of hydrogen. And with hydrothermal cooling, you have a higher difference when you go to higher extension rates. And basically, this is because when you are in very slow, ultra slow spreading regimes, everything is cool already. But when you go higher, the fractures play a higher role. So you have higher feedback from this. And this is just an example of how, when you have this hydrothermal cooling, you have more roughness in the sea bottom, and you have a more variability in the bathymetry than without hydrothermal cooling. So I'm coming back. So, and this is just in the end, we go to bulk numbers. And this is an example of the final state of the model. When you have some peritotide reach, this is well known in the West Siberia margin, which quite relates quite well with the simulation that he got at this point. And all in all, the big number that he got is that the hydrogen production rate is this 7.5 times 10 to the power of 7 moles per kilogram per year per kilogram per kilometer of rift. So he came to this total amount of hydrogen, and then he extrapolated using the first map I showed before to the North Atlantic, and he came to this. This one should be here. So this is total amount. So he divided what he had in the profile by the length of the profile and multiplied by the area, total area, and he got this amount, which is 4.3 times 10 to the power of 18 moles in total. And considering the production rate, which is 30, and it took 30 million years to put the North Atlantic, he came to this amount of production, this 1.4 times 10 to the power of 17 moles per million year. So as a summary, at ultra slow and slow COTs, there's extensive hydration of peridotites, but this is very different from the ones that occurs at mid-ocean reaches. And if this occurs at low temperature, there is a high pervasive initial serpentinization, and most of the hydrogen is related to iron-3 in serpentinite phases, in crostedite or Hessingerite, most of it. Then the big numbers are that the hydrogen production rate was approximately 7.5 times 10 to the power of 7 moles per year per kilometer of rift. And he came to this total amount, accumulation in the opening of the West Siberia margin of Newfoundland. And then he came to this number for the North Atlantic, which is a rate of 1.4 times 10 to a power of 17 moles per million year. So to put this in context, this is 1/4 of the total produced hydrogen by the global system of mid-ocean reaches, as was published by Meredith in 2020. So it gives us an idea of the importance of H2 generation at magma-poor margins, for the importance for the connection for the hydrogenotropic microbial life and hydroxenotropic methanogens, and perhaps as potential energy source. So, and also a global conclusion is that the rate of hydrogen production increases with the rate of extension. So I leave it here.
Thank you, Javier. So we have time for a short question. If someone wants to raise their hand. Sasha, I see that you have one. If you want to ask it.
Yes, thanks. Very nice talk, Javier, very interesting. I noticed that you spoke mostly about the opening of the North Atlantic, so all that hydrogen is long gone. What about the present-day production rates? Do we have to go to ultra-slow spreading ridges, or is there still something coming out of the passive margins that you discussed today?
I mean, it's not in this paper, but if you go to another publications, for example, the one by Elmars, the last drillings of the West Siberia margin show that most of it is heavily serpentinized. There is some samples that are to 100%, other are 60%, maybe on average is about 80% of serpentinization. So what is left over to be serpentinized maybe is about 20%. So this is what we could, if we think about the potential for going, drilling, and forcing water, and producing it artificially, this is what we will have, basically, 20, which is it's still a lot. But a different thing is that it is focalized or not. Is that it was not done by someone, but we need further studies. So how there are these local anomalies, It's like it's something as aluminium. We need 4 times higher to be exploitable, but maybe it's another. It's gold, Maybe much more. So what we need really is to let's assume that we have 20% still there, but then you need to evaluate anomalies, right?
Right. Thanks.